Go ahead.
Okay, thank you for the introduction. So first, I would like to thank the organizers of the ICCP Journal Club for giving me the opportunity to present our work on entrainment mixing processes in convective clouds. The topic of my research is observation-based simultaneous estimation of entrainment and the detrainment rates in convective clouds and their parameterization. Many thanks to the co-authors. As we all know, cumulus clouds play a crucial role in influencing the energy balance of the Earth's atmosphere system and the climate change. Numerical models are now the primary tools for weather and climate prediction. However, accurately representing cumulus clouds within these models is quite challenging. For instance, in Earth system models, the model grid spacing is relatively large, and a single grid point encompasses highly complex physical processes that cannot be fully resolved. Therefore, parameterization of these processes is necessary. Cumulus parameterization is the method by which model represent cumulus processes. In this cumulus parameterization, we consider the various factors that influence cumulus throughout its life cycle, with entrainment and detrainment being among the most critical processes. So this is a schematic diagram of a mass flux scheme, which includes entrainment and detrainment processes of both shallow and deep convection. In this scheme, the entrainment and detrainment rates determine the mass exchange between cloud and the environment. Most schemes are based on this formula, where MF is the mass flux and epsilon is the entrainment rate and the delta is detrainment rate. As pointed out by Bechtold, entrainment and detrainment rates are unknown and can vary in both space and time. So, however, current parameterization for entrainment and detrainment rates involve significant uncertainties, which hinder the improvement of cumulus parameterization. So, how fast is dry air entrained into clouds? This animation shown here illustrates how the entrainment rate affect cloud physics. As you can see, entrainment plays a critical role in cloud development and lifetime. When entrainment is weak, cloud can grow up into a deep convective cloud. However, as the entrainment rate increases, more dry air is mixed into cloud, and the cloud is only able to develop into cumulus congests, shallow cumulus, or may even dissipate. Many previous studies have investigated entrainment rates, including both their estimation and parameterization. For example, researchers have proposed several methods to estimate entrainment rates based on observational data. In addition, entrainment rate parameterization schemes have also been developed using observations and large eddy simulations, such as schemes based on vertical velocity and those based on environmental relative humidity. Together, these studies have greatly improved our overall understanding of entrainment processes. However, focusing only on entrainment is not sufficient. In the real atmosphere, the entrainment mixing processes involves both entrainment and detrainment. Although current convective parameterization schemes do include detrainment, it is often treated in a rather simplified way. Some schemes assume that detrainment occurs only near the cloud top or at the level of net neutral buoyancy. However, during the ascent of cumulus cloud, lateral detrainment around the cloud edge still plays an important role and deserves special attention. Fortunately, the, the importance of detrainment has also been recognized by several studies. Previous work have made some attempts to estimate and parameterize detrainment rates. For example, Barrow et al. Calculated the vertical profiles of detrainment rate using the equation shown on the left based on the Bank-Plon approach. And Debbie and Austin, on the other hand, estimate the detrainment rate using a direct measurement approach, which use this formula. However, both approaches can currently obtain detrainment rate only from numerical simulations. The key limitation is that there is still a lack of method for estimating the detrainment rates from observational data. So improving the parameterization for entrainment and detrainment rates begins with a reliable approach to estimate these rates. Currently, the commonly used approaches are the Bank-Plon approach, the mixing fraction approach, and the direct measurement approach. However, as you can see, while the first two approaches can be applied to both observation and the model simulations, they cannot estimate detrainment rate from observations. The direct measurement approach, on the other hand, is only feasible within numerical models. Therefore, the scientific question I aim to address is that the current observation-based approaches cannot obtain detrainment rates directly from observations. So to address this challenge, we developed a new approach to solve this problem. In this work, we developed an approach for the simultaneous estimation of entrainment and detrainment rates. This approach builds upon the theoretical framework proposed by Nogren et al., which assumes that the cloud properties measured by an aircraft, denoted as MC, result from the contributions of three components: the adiabatic cloud MA, the entrained air ME, and the detrained air MD during ascent. By leveraging the definitions of entrainment and detrainment rates, coupled with the conservation equations for cloud mass, total water, and total energy, we derived explicit formulas for calculating both the entrainment and detrainment rates. Here, H represents the height above cloud base. MA, ME, and MD represent the mass fractions of adiabatic cloud, entrained air, and detrained air, respectively. So before applying the simultaneous estimation approach to observational data, we first evaluated its performance. Our assessment consists of three parts. First, we evaluated this approach using aircraft observations. We derived a formula that links in-cloud variables to entrainment and detrainment rates. By applying our calculated entrainment and detrainment rates to this formula, we can compute moist static energy and total water. A comparison between these computed values and the corresponding observations reveals a strong agreement. This consistency shows that entrainment and detrainment rate estimated from the simultaneous estimation approach can effectively reproduce the observed cloud thermodynamical properties. Second, we evaluated the simultaneous estimation approach using the explicit mixing puzzle model. Here is the process of the EMPM operation. A cloud ascends adiabatically above the cloud base and reaches a specific height where entrainment occurs. The subsaturated entrained air replaces a same-sized segment of the cloud puzzle. And the cloudy air that has been replaced is detrained into the environment. The cloudy air and the newly entrained subsaturated air subsequently undergo turbulent mixing processes. Importantly, the EMPM allows us to prescribe the entrainment and detrainment rate. This control enables us to use the cloud properties before and after the entrainment events to back calculate the predetermined entrainment and detrainment rates. Our simulations conducted under various conditions consistently show that the simultaneous estimation approach can accurately back calculate these predetermined entrainment and detrainment rates. Finally, we evaluated the simultaneous estimation approach using large AD simulations. The wolf-less employed a horizontal grid spacing of 50 meters and a vertical grid spacing of 30 meters, with a total simulation time of 5 hours. From the simulation output, we identified cloud grid points and their surrounding environmental grid points. Then we applied both the simultaneous estimation approach and the traditional approach to the simulation results. The figure on the right shows the vertical profiles of estimated entrainment and detrainment rates. The red line shows the traditional approach, and the black line represents the simultaneous estimation approach. As you can see, both approaches yield very similar entrainment rate profiles. While some differences are observed in the detrainment rate profiles, the overall vertical distribution remains consistent. These results further support the reliability of our simultaneous estimation approach. So it's important to acknowledge that our new approach relies on assumptions regarding the source of entrained air and the detrained air. So to assess the sensitivity to these assumptions, we conducted a series of sensitivity tests. Our results show that as the entrained air originates from a greater distance from the cloud edge, both the entrainment and the detrainment rate decreases. However, it's noteworthy that the detrainment rate estimated by our new approach exhibits less sensitivity to the source of entrained air compared to the traditional one. So furthermore, regarding the assumption of detrained air properties, as the entrained air more closely resembles the ambient air, the detrainment rate decreases, while the entrainment rate remains unaffected. So after thoroughly evaluating our new approach, we have started to apply it to observations. Given the significant impact of aerosol cloud interactions on convective processes, previous studies have provided mainly qualitative explanations of how aerosols affect entrainment rate. But quantitatively, observational evidence has been lacking. To address this gap, we applied the simultaneous estimation approach to the aircraft observations from two field campaigns, Recall and Classic. We try to quantitatively examine the impact of aerosol on entrainment rates. As shown in the figure, in both field campaigns, the entrainment rate is negatively correlated with aerosol concentration. We find that this relationship can be well fitted by a power law function, and it also passes the statistical significance test. These results indicate that increasing aerosol concentrations separate the entrainment rate. In contrast, we do not find a clear relationship between detrainment rate and aerosol concentration. Therefore, we focus on the physical mechanisms by which aerosols influence the entrainment rate. We find that aerosol affects the entrainment rate through the following physical mechanism. An increase in aerosol concentration leads to smaller cloud droplets. Near the cloud boundary, these smaller cloud droplets evaporated more efficiently, which enhances evaporative cooling. Stronger evaporative cooling generates stronger negative buoyancy around the cloud, increasing the buoyancy gradient and the updraft vertical velocity within the cloud. As the vertical velocity increases, the interaction time between the cloud and the environment is reduced, which in turn suppresses entrainment rate. As shown in the figure, higher aerosol number concentrations are associated with larger buoyancy gradient and stronger vertical velocities, while stronger vertical velocity correspond to lower entrainment rates. Further analysis shows that the negative correlation between entrainment rate and aerosol concentration exists for both small and larger clouds, indicating that cloud mass does not significantly alter the suppressing effect of aerosols on entrainment rate. However, this separation is more pronounced in smaller convective clouds, mainly because smaller clouds with smaller adiabatic cores are more susceptible to entrainment. In addition to aircraft observations, we also applied the simultaneous estimation approach to global satellite observations. Using cloud products retrieved from the SMPP satellite during June to August in 2017, we estimated global entrainment and detrainment rates. As this represents the first application of the simultaneous estimation approach to satellite observations, we validated the satellite-derived results using aircraft observations to ensure consistency in sampling conditions. Aircraft observations from the same season were selected for comparison. The probability distribution functions of the entrainment rate from both satellite and aircraft observations peaks in the second beam, while those of the detrainment rate peaks in the first beam, indicating strong consistency between the two datasets. This result demonstrates the reliability of estimating entrainment and detrainment rates from satellite observations. So the figure on the left displays the time averaged entrainment and detrainment rates. On the right, we present latitudinal variations of entrainment and detrainment rates, as well as a comparison between the northern and southern hemisphere. It can be seen that the differences between the two hemispheres are small. However, both entrainment and detrainment rates tend to increase with latitude. The relatively low values near the equator are attributed to the vigorous development of cumulus clouds in tropical regions. Here we show the land-ocean contrast in entrainment and detrainment rates. Both entrainment and detrainment rates are higher over ocean than over land. This significant contrast arises from the distinct characteristics of cumulus clouds over land and over ocean. Over land, cumulus clouds typically have stronger convective cores, which are more effective at preventing the dilution of entrained air. Considering the significant latitudinal variations in entrainment and detrainment rates, the land-ocean contrast may be affected by the geographic distribution of cumulus samples. We attempt to isolate the impact of latitudinal variations on the land-ocean contrast. This result reveals that a pronounced land-ocean contrast persists within fixed latitudinal ranges. After obtaining the global satellite or global satellite-based entrainment and detrainment dataset, we attempt to develop the parameterizations using this dataset. So first, we tried the traditional physical approach, we tested three different fitting equations for entrainment rates with variables including environmental relative humidity and vertical velocity. For detrainment rate, we tested six fitting equations using variables such as entrainment rate and environmental relative humidity. Here, the x-axis shows the entrainment and the detrainment rates calculated from satellite observations, which we treated as a true value for comparison. The y-axis shows the entrainment and the detrainment rates obtained from the parameterization using the test dataset based on our fitting results. Overall, we recommend using environmental relative humidity and vertical velocity to parameterize entrainment rates, and using a parameterization based on entrainment rate and environmental relative humidity for detrainment rate. Second, we also applied machine learning approach to predict entrainment and detrainment rates. For the machine learning approach, the results are more tightly distributed along this line, indicating that machine learning can accurately predict entrainment and detrainment rates. We further interpreted the results using the sharply additive explanations analysis in the scatter plots of each feature based on the sharp analysis from top to bottom. The variables are ranked by their importance in predicting entrainment and detrainment rates. The color represents the magnitude of each feature, and the x-axis shows the sharp value with positive and negative values indicating whether the feature increases or decreases the predict entrainment and detrainment rate. Sorry. As shown in the figure, environmental specific humidity, relative humidity, and temperature contribute most to the prediction of entrainment rate. And the entrainment rate is positively correlated with the environmental specific humidity and the relative humidity, which is consistent with the physical expectations. Machine learning also accurately predict detrainment rate, and from the sharp plot, entrainment rate is the most important contributor, showing a positive correlation with detrainment rate. Finally, we compared the parameterization results from the physical approach and the machine learning approach. Here we show the mean absolute error, mean squared error, and the root mean squared error for the different parameterization schemes. For both entrainment and detrainment rates, the machine learning approach achieves the lowest errors. This demonstrated that machine learning approach has an advantage over physical approach for developing entrainment and detrainment rate parameterizations. The likely reason is that physical approach cannot account for the combined effects of many influencing factors, whereas machine learning can capture complex nonlinear relationship between variables through data training. So far, I have introduced the development, evaluation, and the application of our simultaneous estimation approach. It's important to note that everything I have discussed so far focuses on shallow convective clouds. Now the question is, can this approach be extended to deep convective clouds? So first, let's quickly review this approach. By leveraging the definitions of entrainment and detrainment rates coupled with these three conservation equations, we derived these formulas for calculating entrainment and detrainment rates. This approach can estimate detrainment rate from observations. However, it's only applicable to shallow convective clouds. To extend this approach to deep convective clouds, the major challenge we face is that the presence of precipitation in deep convection leads to a violation of the total water conservation equation. To address this issue, we draw inspiration from the treatment of precipitation processes in convective parameterization schemes. Specifically, we consider the effect of liquid phase and ice phase precipitation using the modified set of conservation equations. We can now estimate the entrainment and detrainment rates of deep convective clouds based on their observational data. We call this method the PE-based approach, where PE stands for precipitation efficiency. Since no other observation-based approaches are currently available to estimate the detrainment rate of deep convective clouds, we're using numerical simulations results to evaluate the reliability of our new approach. Here we employed WRF simulations with a horizontal resolution of 480 meters and 60 vertical layers. From the simulation output, we identified cloud grid points and their surrounding environmental grid points. Then, entrainment and detrainment rates were calculated using both the PE-based approach and the bound-prone approach. The figure on the right shows the vertical profiles of the estimated entrainment and detrainment rates, where blue represent the PE-based approach and the red represent the bound-prone approach. As you can see, the vertical profiles derived from the PE-based approach are consistent with those from the bound-prone approach in both magnitude and vertical distribution, confirming the reliability of the proposed approach. It's important to acknowledge that our new approach relies on several assumptions, including the presumed entrained air properties and the detrained air properties and the precipitation efficiency. We conducted a series of sensitivity tests on these assumptions. Our results show that the variations of the presumed properties of entrained air have a minimal impact on their estimation of entrainment and detrainment rates, especially when the entrained air is sampled at distance greater than 1,440 meters from the cloud edge. As the fraction of in-cloud air in detrained air properties increases, while the estimated detrainment rate increases, while the estimated entrainment rate remains unaffected. So for the precipitation efficiency, higher precipitation efficiency results in an increased entrainment and detrainment rates, with a more pronounced increase in detrainment rate. We further conducted a quantitative evaluation of the sensitivity test using the results from the bound-prone approach as a reference. The colors here in the figure represents the relative root mean squared error of the estimated entrainment and detrainment rate from the PE-based approach. As the solid dots indicate the minimal error, the Quantitative results show that variations in the properties of entrained air have a relatively small impact on the error. When the precipitation efficiency is set to 0.005 per meter, the PE-based approach provides the most reliable estimate of the entrainment and the detrainment rate. Based on aircraft observations of deep convective clouds, we estimated the entrainment and detrainment rates. This figure shows the probability distribution functions of entrainment and detrainment rates. As you can see, both entrainment and detrainment rates exhibit unimodal distributions. Overall, the observed detrainment rate exceed entrainment rate in these deep convective cloud observations. The magnitude of the estimated entrainment and detrainment rates are comparable to those reported for deep convective clouds in previous studies based on numerical simulations. So to conclude, we have conducted a comprehensive evaluation of the newly developed simultaneous estimation approach for entrainment and detrainment rates and confirmed its reliability. Using aircraft observations, we revealed the impact of aerosols on entrainment and detrainment rates. We also applied the approach to global satellite observations to investigate the global distribution patterns and the land-ocean contrasts on entrainment and detrainment rates. Moreover, this new approach has been extended to deep convective clouds. In the future, we will apply this approach to a broader range of observational datasets to construct a long-term dataset of entrainment and detrainment rates, which can be used for parameterizations, improvement, and model evaluation. That's all for my talk. Thank you.